This is production through a fermion loop.
Yeah.
Glue, fermion loop.
Yeah.
Triangle.
Yeah.
So the amplitude's going to go as the mass, right?
That's probably 1 over mass squared.
Yes.
Or sorry, no.
So at those irrelevant energies, all those S, C, D, and U are basically going to be massless.
Yeah.
The only place their mass would really factor in is with the coupling case.
Oh, okay. So that'll come
So
with
then
once.
you look at what
Yeah.
So I would expect
So what's the ratio of the top mass to the charm mass?
top to charm.
Yeah.
It's about a factor of 130. I mean, it depends what you mean by the top mass, right? But it's about a factor of 130. So I would mention the charm would be the place to start. Because charm's mass is comparable to bottom. I don't know. So it makes sense that if you're considering bottoms, you might want to consider charm.
Yeah, that's what I'm really trying to do right now is to first figure out how all these things work. So when you get your numbers, what kind of issues you plug these numbers in, they have all the Yukawa couplings to be set to zero. Like except for top and bottom, the rest are set to zero.
Right.
But then you actually can't really put some random numbers there. You need to know what numbers to put and where to put and how to generate the Feynman rules for all of those and then to use those Feynman rules to get the answers. So right now it's just really about first trying to figure out how all of these things work and then once I figure that out, I'll give them some numbers and then see if he knows the numbers better. If they make any sense now. And if he says, well, this is bullshit, then either I recheck the numbers or I figure out this is bullshit indeed. And it's 99 out of 100 things that theory people try and do.
So basically the
If it's not bullshit, then I learn more point of view theory and see if there is some model that works for it.
And then
That's the thing.
Yeah.
So right now the idea is to first learn how these simple packages work in different rules. MATLAB is very easy, but MATLAB gets annoying when you have to like put in a parameter card into it. And to put the parameter card into it, you use find rules first.
so we're thinking about having a meeting of us together, the small committee for that day, and then either
Loads of the results, generate, process, which I find very annoying actually because it's nice if you know the subject, it's not nice if you don't.
That's why that works.
And it's very cool if you know QT, I'm doing
Just plug it in. I don't feel like doing 3 new calculations.
But on the other hand, I'm like a second year graduate student. So I go like, oh, I'm cheating.
Gotta earn your stripes. Do one.
I'm cheating. I can't just go like, generate process. It just feels like cheating.
I haven't
Then, I
talked
mean, I need
to
to-
Michael yet. Is that or I guess, so when do I need to do that by? Is there like are there action items for the
The committee's don't need to meet.
we just have to sort of have an idea of what we want to talk about?
Yeah, and then people can contact you with ideas and stuff.
Dan, you saw
It's organized.
DB.
Yo,
You saw the minutes, right?
yeah, I'm still catching up. I'm a little behind.
It's fine.
But yeah, it looks good.
First order of business: get more pizza next time.
Yeah, I heard there wasn't enough.
It's
People
like 2
didn't
or 3
fill out.
people came and figured it out.
People didn't fill out the survey.
Did they? Yeah.
You should have had a thing where the people who fill out the survey got pizza.
It was anonymous.
Oh,
Yeah.
damn it.
Do you want
Pretty
pizza, yes or
mean.
not? And also, what is your name?
I even doubled.
Pretty mean though.
And what is
I don't
your-
know.
I even
You asked
doubled
me.
the number of responses to the survey.
Well, because about 10 people responded after you got the number.
Yeah.
You were too slow getting me the number.
No, I gave you the number. I gave you the number as it was when it was.
Well, that was
and then
when
more
Liz
people
requested
responded.
the number of people that she needed to order for. So
Yeah. We had 30 people and
Assholes
6
replied.
pies. So
30 people. Okay, so everyone got a slice.
No.
No.
in
The people
principle,
who
everybody
came
should
late
have
did
gotten.
not get slices.
That's.
You did not pay sex at all.
Well, at least it was a turnout. That's good.
Yeah, that was encouraging.
Was the atmosphere good? People seemed
No. Toxic. Awful.
toxic. People took away like it's a good thing.
Yeah, I think so. I already have many ideas for how to think about the TA.
Oh, good. Yeah, you're a good choice for that.
Super TA after all.
But that committee already exists. Things already putting together, so we don't need to make one.
Did you punch him? Did you shoot?
He is so full of it sometimes. No.
Should I get started?
Yeah, go ahead.
Sorry.
Yeah, we're.
Jeff, you're in charge.
Am I?
Sorry.
It'll be a 5 minutes podcast.
So, okay, guys. So, today I want to talk about quantum correlation, and it's in a graph theory platform. But before that, the real motivation behind this talk, the big question behind this is actually this: is quantum mechanics a complete description of the nature? And because quantum mechanics is almost in every sub-discipline in physics, modern physics today, condensed matter, high energy, and almost anything non-classical is quantum. So it's really a question we should ask ourselves. And hopefully, after this talk, we can have a little bit more insight of this question. Okay, so the main idea of this work is that the causality structure of the nature can be described by a graph platform. And more precisely, before whom know a little bit about the graph theory, the graph simply contains the vertex and the linkage or hinge between them. So that's the argument I want to make. It's like the event and the measurement can be represented by the vertex, and their relationships can be present by the linkage among them. That is the main motivation and main platform for the whole work. So, any question before I proceed? No? Okay, so to be more precise, actually in the graph theory, in the math realm of the graph theory, there's a lot of important theorems and definition. More precisely, there's an independent number. Some other numbers can be defined for a graph. And I will claim that those numbers are precisely correspondent to the different theories in the sense of the maximal correlations. Yes, and I will call this thing a graph platform. But before we really go to that platform, I need to give you guys some preliminary information to pave the road to the graph platform, which is the EPR paradox and Bell's inequalities. So the EPR, the first E absolutely stands for the Einstein, and that's a very famous paradox. And the Bell's theorem is actually the most famous no-go theorem in the physics. Okay, so that's the so it's like the structure of my talk. It's like how what stuff I will cover in this talk. So I don't want you guys to lose. So before I really go to the stuff. Well, okay, let's return to the first question I asked in the very beginning. And actually, fundamentally, there's two kind of view for this question. One is favored by Einstein, by his famous quote, God do not dice. So in that interpretation, the physical system do have the attributions before the measurement, and it's all predefined. It's just quantum mechanics, not good enough. It's good in the sense it can give you like a statistical distribution, the probabilities of what's going to happen. But it's not good enough to give you the full picture. That's the way shared by like famous physicists like Schrödinger's. No, the famous physicist like Einstein. Wait, so the Einstein favors the wheel is not good, it's incomplete. But in another sense, there's also a branch of physicists believe that it's not in the sense that the quantum mechanics is not complete. It's just the measurement can disturb the very state of the physical system. And this view are shared by famous physicists like Schrödinger by his Schrödinger's cat thought experiment or whatever. The main idea is measurement can create that very purpose. So actually there's two conflicting views there. And as I said before, the Einstein really favored the first one because they think the quantum mechanics is incomplete. So in 1935, Einstein, I don't really know how to pronounce that, and Rosen published their famous EPR paradox. Just try to argue for their favor. So what's the claim? Let's just consider a very simple experiment. There's a pion, and we are all in the center mass system, center mass coordinate of this pion. Or equivalently speaking, the pion, the neutral pion is just stable, just don't move. And then it decays to an electron and a positron. What gonna happen is because of the momentum conservation, angular momentum conservation, what you really can get is a state like this. If the electron have the spin up, the positron must have spin down, and vice versa. That's just required by the conservation laws. So why would this bother you? It's because the correlations between those two sets of data. Like for example, if I can draw some like pseudo data there. Here's for the spin for the electron, and here is the spin for the positron. If it's 1, it's negative 1. 1, negative 1. Negative 1, it must be 1. That's the conservation law. So in this sense, the data are correlated to each other. So what's the definition of the quantum correlations? It's just in the sense that the data are correlated. You can just think about the quantum correlation as a statistical correlation. Although in this specific scenario, it's perfectly anti-correlated. But it doesn't matter, right? It's just so my claim is the quantum correlation is just the statistical correlation. So any questions before I proceed? Nope. Okay. Yeah. And as far as we get this correlation here, the paradox emerged. So let's consider those two electron. So here's the pion initially here, right? They decay to the electron and positron. Let's say if it's after a very long time, and those electron and this electron and positron have a very far space-like distance, like a galaxy's distance. So in modern terminology, that means they have the space-like separations.
Is that possible? How can two things that originate in a point have a space-like separation? Seems impossible to me.
Time-like separation.
Time-like, yes, space-like, no.
Okay.
If the events where you measure them are space-like, I think is the
Oh, that's
is the
possible,
claim.
yes, but the two objects in themselves are not space.
Oh, right. Yeah,
Right.
that's the point. So if they so the point is they just in the different positions, and you consider the lifetime of those electrons and positrons. The problem is we want to maintain the locality of the system. That's the that's the point of the causality. But if you really do a measurement here and you know the spin of the electron, you immediately know the information of the configuration for the positron. So that's then you should have a sense of not okay. And actually, the Einstein called this spook action at a distance, and it just means there's some information traveled faster than speed of light. So that's the point of that's prohibited. That's not okay, right? So that's why it's called a paradox. So it's the famous EPR paradox. So any questions so far? Okay, so the point the Einstein really want to make is not that he want to throw away quantum mechanics. What he really want to say is that quantum mechanics is incomplete. So there's a lot of effort want to complete kind of incomplete theory. And the guess is that there might be a hidden variable. So there's a lot of different theory called hidden variable theories. And for the hidden variable, because the name is come from no one really know what variable it is. It's like dark matter. No one know what is dark matter. So just use a placeholder to put there and call it lambda. And but there's a genius called Bill, and he said there's no local hidden variable theory is compatible with the quantum mechanics. That's a very famous no-go theory. It means some physical situation is impossible. And surprisingly, his argument is very, very natural and not very sophisticated compared to the theorem he's going to argue. And what he really taught is like a generalized EPR experiment. And we will see. So here is the generalized EPR experiment. So you might say there's a vector A and vector B here. If the vector A and the vector B are in the same direction, we recover the original EPR experiment, which means the spins are perfectly anti-correlated. So the thought is that maybe we can change the direction. We circle around the correct direction of measure the spin. And there might be something interesting. Like for example, if I just define B as the negative A, so it just like the chart over here, what you should get is like every time it's spin up, it's spin down, but spin down is just in the same direction as this. So it's always like 1, 1, 1, 1, negative 1, negative 1. this sense, you really want to think is like, can we get something useful if I just define the arbitrary ANB instead of the perfect correlation or anti-correlation? So, so let's say if there's a, I just define it in this way. So they are not parallel or anti-parallel. The position of the, the spin of the electron and positron, and their product should like this. -1, -1 is -1, -1, but sometimes it can be all be -1 and +1, and then some randomize the correlations. So the idea is that if I define the average of the product, the summation, the average of the products of all the experiment I did, which can be written as P equals to AI BI. So AI1, B1, A2, B2. So it's the product. It's just like sum this over and it takes the average. What we get is like first, for the parallel one, we should always recover to the negative one. That just means they are in different spin. And for the anti-parallel one, it should be 1. And in general, the quantum mechanic predicts it's really the negative A times B. So the A and B are the positions as defined in the chart. So there's rigorous proof for this in the quantum mechanics, but it's going too detailed. We still have the graph platform to go, right? So I don't want to prove this. But if you really think this is like the different coordinate of the AI BI just timed, which just like the definition of the inner product, right? So it won't bother you too much, right? So I'm concerned before. Okay. So it's the same one, right? Now let's do some assumptions and prove the hidden variable theory is not physical. So first, suppose there's a hidden variable lambda. No really assumption about this hidden variable. It can be whatever random variable it could be. And also the locality assumption that the result of the electron measurement is independent to each other. That's otherwise, if this correlated is related, you can write something down like this.
So sorry, can you remind us which detectors get in the electron and which is getting the positron? I didn't make a mental note of that. So your B and A, which way is electron? Can you just show that picture from your slides again briefly?
So you mean?
No, can you show the slides again briefly?
You mean
Yes, this one. So the positron goes through B and the electron goes through A.
Oh yes.
Okay, thanks.
Great. So let's do a little bit algebra there, and we can prove the famous Bell's inequalities. So the first point is still we need to recover the most simple case, which is suppose there is a function a and it depends on the position of your like the direction of your measurement and the local hidden variable there. It must be positive or negative one. Means the result, the experimental result must be spin up or spin down, right? And the same for the polytrons. And the point is, if the measurement have the same position, so it's the same, they are in the same directions. They should be same. I mean, they are anti-correlated, just spin up, spin down. Right? So there's, it is, in a sense, the hidden variable can make a difference there. It must be in different spin direction.
So sorry, I'm a little bit lost. So your capital B is a function of vector A, or is that supposed to be a function of vector B on the third line?
In the third line?
Yeah.
Yes. My point is that if you can just think of A and B as a machinery to get you the answer of the spin, right? And my claim is if they are in the same direction.
You know, the answer is, the statement there on the third line is, there should be minus B evaluated at B equals A vector. So the A vector next to B is supposed to mean when the B vector is equal to the A vector.
Yes, so it's just like that, just in the, you just measure the same direction, and no matter the hidden variable is what, you always get the anti-correlated relationship between the spin of the positron and the electron.
But is A and B the actual values of the electron and positron spin, or is it a direction in space?
Yes, I should define this. Spin is like this. It's like the definition.
No, A is a direction in space.
Okay.
It's like the Z axis.
Okay, fine.
The first one is the electron spin, and second is the positron spin.
Yes. Yes.
Can I imagine this way? A is the detector of electron. That's the result of electron detector coming out. So there's only two possible that the detector
Yes.
can tell you positive one and negative one.
Yes.
And if our any factor A in the capital A is the direction of detector. Okay. Yes.
Okay, so let's use the definition there to recover like what is the P, A, and B. So remember, in the previous case, it's just equal to the negative direction. We still remember this, right? Yep. And in terms of the A and B, what we should get is there's actually a probability density depend on the hidden variable, and A be like this. And the only assumption which is like trivial is that the probability density should be 1. So you can just think of this as so if you even remember the very like the definition at the very beginning, it's like I shouldn't erase that like this, right? It's just like you have a summation at first, and you replace it by a integration, and you only count in terms of the hidden variable. That's it's like a natural transition we always use, right? And it's if the hidden variable in this range you count this, and then in another range you just do the summation at that range. So, any questions? Okay. So that's really something interesting, and I will use that identity to prove, like it's like you just yes, you just do some algebra. I will write it down. Is the same as this. Wait, is this the same?
Yeah.
Oh, I don't know what happened. Oh, never mind. Oh no, I just made a mistake. It's not the A. So you just do a substitution, right, for the piece, right? And what you can do then is like consider another one as the AC. So three vectors, a new orientation of the direction. And what you really want to think is like minus the AC way. And what you can get is something like a lambda minus right? So just the same logic. I'm gonna go here. And the point is you time extra factor 1 here. And this 1 is just this. Because what you really think is to factor something out, right? That's how the inequalities goes here. Because the only two values is 1 or -1, and its square must be 1, so it's the same. And you just extract some factors out of this. You recover something like so it's still this equal to minus times the factors this. Right? Just simple algebra. And what you try to say is that this one must be larger than -1 and smaller than 1 because of the definition here. And there's something really interesting. What you really can get is, so you just try to think this and this, the 1 are out, okay? It's like a definition of a new something, a new product of, actually it's B and C, right? Just follow the definition there. So I think I don't need to write the final line, and because I already read it here, that's the Bell's inequality. That's it. And how can this inequality prove, not prove, says that the quantum mechanics are incomparable with this result? We just think about a very simple scenario. So my definition of the ABC are just like the figures. A and B are perpendicular and C is just 45 degrees to each other. And you do some simple algebra. And it's in physical, it's not physical. That's it. That's the inequality. So any questions before I go? No. So Bell's theorem is the no-go theorem, and no local hidden variable is comparable with the quantum mechanics, which really motivates the work I really want to talk today. And the motivation is here. After a no-go theory, we still want to try to find something can describe the causality structure of our nature, or at least the correlation structure, right? So it's mathematicians may be thinking another way, like to turn inequality to quality, right? So that's something we could think about, and that actually lead to the graph theory. So the graph theory just start from Euler's work. It's like there's different lines there and different crazy geo configuration. I think it's in England, but I'm not sure. And there's bridge and land. And the Euler's real insight is that he can turn something about to this abstract something. The point is, it doesn't matter how big is the land. It's just a point, and the shape of the bridge also doesn't matter. You just, if they are related or there's a bridge, you can pass by, and that's it. So the motivation is that if we can do the abstractions to turn this to this, can we turn the measurement or events and their relationship to something similar to that? Yeah, so that's the point. So actually, we always use the measurement a lot, but in the modern terminologies, measurement is kind of the man in interpreting the state of the quantum mechanics. So sometimes people really to use even, but it's the same idea. And the point is, instead of if two events are correlated, you you assign an age to them. That's not the idea we will do. What we really do is that if they are exclusive, we draw a line between them. So you might ask, why is that? The really convenient is that the mutual exclusive event can exceed one. I mean the probabilities. Actually, the secret is that it doesn't matter. You can do the previous one as that. Because actually in the graph theory, you can always get the complement graph of a graph, and it's like the homomorphism or push forward some mathematical structure inside. But we just adopt the basic view. Okay, so I will get started to look at the graph theory transform. Maybe I already mentioned it before. This one is called the bad drawing, the magic pentagon. And before I make something too mathematical and abstract, I really want to use the simple graph to demonstrate the point. So let's consider a graph like this, and the vertex are labeled. So we can use it to call their names. And I use sorry. Stupid. Anyway, and the probabilities associated. Oh. Anyway, you know what I mean, right? So, but for the classical one, so yes, first I want to talk about the classical theory. So, you just think of 5 measurements, and they are mutually exclusive, and you are in a realm of the classical mechanics. So, everything can either happen or not happen. What can you get from it? Let's suppose this one happened, okay? And this one can happen because there's a line, right? So what else can you get? You can just pick whatever line.
So a line connecting two of these means that they're exclusive?
Yes.
Okay.
It is not powerful as the classical realm, but when we go into the more general theory and quantum mechanics, it will work.
But here, then that means that these are only pairwise exclusive. They're not all mutually exclusive.
No, like for example, this one and this one, there's no line there, so it's not transitive. Yeah, so the maximal number is 2. Actually, there's really a definition called independent number in the graph theory. You know, this graph platform of the quantum correlation is very new work, like within 3 years. Yes, that's true. But those like independence number and other numbers defined in graph theory has a long history and has its own meaning in the graph theory. But it just happened that for this specific graph, this 2 is really the definition of the independent number, which means the maximal set of vertices that are not adjacent. Because they are not adjacent, you can always let them all happen, and it doesn't affect you. There's no way to violate the exclusive principle there. That's any questions before I go? So that's almost trivial, right? So maybe some other theory will give you some interesting result. So next we are going to talk about the more generalized theory. Not go to this slide. So in the more generalized theory, you are associating the probabilities there. And what you want to achieve is the summation of all the probabilities going to maximum. And a cheating way of doing that is you associate 1/2 to everything. And like for example, 1/2 and 1/2 is still less than 1. So the exclusive principle still holds, right? And what can you get from this specific graph is 2.5. So it's like classical mechanics. It's a generalized theory. I don't know what the name. So there's also a definition in the graph theory. Call this number a fractional packing number. The definition is just followed by this. It is really what we want, right? You go to the maximum, and the only constraint is that the exclusive, I mean the mutually exclude even, the probability of them can exceed 1, like here. So that's the more generalized theorem. So you get 2.5 for this specific graph, pentagon, magic pentagon. And we're going to the quantum mechanics. Does everyone would like to volunteer a guess? What's the number? It must lesser than 2.5, right? But maybe bigger than 2. And it's a pentagon, right? So any ideas? No ideas?
Sorry, I have a question. So, in the middle, there's I don't know the word, but below that word is 2.5.
What? This bar?
Yeah. So, you get that basically you sum over all the possibility around the
Yes.
Yeah. But so if I want to, and that is a fractional packing number, right?
Yes.
So if I want to know the fractional packing number of quantum mechanics, I need to know
Generalized theory, not quantum mechanics.
pure
We haven't discussed quantum mechanics yet.
Okay,
It's a
but-
different number.
Oh yeah, but you want us to take a guess, right?
Yes.
Yeah, but how can I take a guess if I don't know what probability associated with each point?
You want to achieve the maximal value.
But
So it's at you have the choice to assign, as long as the exclusive principle is guaranteed. So I will write down the answer.
Oh,
It's very
is
fun.
that a number? Oh.
I'm sorry, I'm too emotional. Square 5.
So can you tell us what the rules of the game are? Because I have no idea what just happened.
Yeah.
So, I mean, I think I understand the first column there.
Right,
I can convince myself that I can understand the second one.
I can, so we could start there too. The 2.5 isn't clear to me.
Oh, so the 2.5 just you try to get the maximum value of P1 plus P2 plus P3. All the sum over all the
You know,
probabilities.
but I think what's missing is that you didn't tell us what the rules of the game are. So the point is, what I suspect is happening is that if you assign some probability for the event associated with V0, and you call that P0, then the probability associated to the adjacent vertices are 1 minus P0. Is that correct? Or no?
Oh, right. I should mention that. Yes, very good question.
Or is it less than that?
Less
I think it's less.
than.
The only principle we need to satisfy, we need to guarantee is that the mutual, sum of the probabilities of exclusive event can exceed 1.
Okay,
That's,
good.
that's the only rule.
Right, so that means that if the probability of event 0 is P0, then P1 is less than 1 minus P0,
Yes.
and P4 is also less than 1 minus P0. Right?
Yeah. P3 you mean this one?
Four.
Oh yes, yes.
But how do you get P2 and P3?
I mean,
You know, and then he's asking us, what's the largest number you can get for the sum of all these probabilities?
it's more like this. I would stay this place. Let's say.
Yeah, sorry, less than equal. Yeah, that's what I meant, yeah.
Right.
Yeah, that's what I meant.
Oh,
And so on.
So as long as there's a line.
No, that I understand. And then what you're doing for column 2 is that you're asking us, given all these rules, what's the largest value I can get for the sum of the probabilities?
Yes.
And then I can buy that the 2.5 is correct.
But the 2 obtains if you set P0 to 0 or 1.
The
That's the
two,
one we
yeah,
had class
the two is what happens when you're making measurements.
That's why it's either 0 or 1,
Exactly.
Yeah. So the 2 is when you actually try to do the experiment. And you say, oh, this didn't happen, then that still could happen. And then you try to maximize the probability, the sum of the probabilities.
But having P0 and P1 both not 0 means they're not exclusive in the classical sense. So classical means that you have
That's correct, yeah.
consecutively ones and zeros going around.
Yeah. But now I don't know what quantum mechanical means.
So is it-
Also, can I ask, so why, it's not clear to me that you can always just put 1 half at every vertex no matter what graph you give me. And then number is just,
That won't be true.
it isn't.
No, it's all subject to what you have edges. So if you have something that has 2 adjacent vertices, say you added a leg between V0 and V2, then that you couldn't have 1 half at all 3 of them.
Oh, sorry, of course, because now V0.
That was my
Gotcha.
Probably
Okay, gotcha.
I have a question.
Sure.
So when you're drawing an edge between P0 or V0 and V1, is it correct to say that there's some measurement that you're making, and then the answer you get is either V0 or V1? Is that the meaning of these lines? If they're exclusive, that means that I make some measurement and those are my 2 exclusive options, or is that not correct?
A simple example, like you have a dice,
Mhm.
and it's like 1, 2, 3, 4, 5.
Okay. In that case, then, so if I have a 6-sided die that I'm rolling, I would have 6 vertices that are all connected to each other because they're all mutually exclusive.
Yes, that's stronger than this. It's just partially that.
So that would be the classical one, which you described.
Okay.
5-sided die.
Right, so that
But
would,
then
so
you
that-
could assign a probability to each vertex of a 6, and then find out that you get 1 for
Okay.
as well, I think.
So I don't have to worry about the fact that if P0 is a third and P1 is a third, I'm not losing a third of probability somewhere. Whatever that even means.
Okay. So.
Oh, so you're saying that those are the only, P0 and P1 are exclusive and they are the only result possible, is what you're suggesting.
Right, exactly. So they talk about, in the paper, they talk about there's tests. And for the test, I either get a 0 or a 1. And those are my only 2 options. But if there's a test with 0, 1, and 2,
When we go into the quantum, it should be all clear because I make a specific example. Like there's a state, and you have your A, B, C, D in different directions. It's more like a projection. Okay, so I will go to this one before. Yeah, sure.
In your graph, all the vertices has the probability of a half, right?
Right.
Can I understand that when V not happens, V2 has to be happening?
That's classical.
I mean the classical.
That's.
Yeah, I'm considered the classical one. So in
Yes.
your probability, when V0 happens,
So in the
V2 has to be happening.
So yeah, I will make this explicit, I think. In terms of the classical mechanics, you have one more constraint, is that P is only can be 0 or 1. So that's kind of constraint.
I mean in general, because you assign a probability to each vertex.
Yes, so it only can be 1 or 0. That's the meaning of the classical. It's different, right? So it's like general theory, you have almost no constraint. And for the classical mechanic, you have a very strong constraint. And the real point is that the quantum mechanic is in between. It's very strange.
But your general case is also in between.
What?
The general case, all the
Oh, I mean
vertices
the
are-
quantum mechanic is in between those 2 cases.
Okay, now you proceed.
Okay. Sure. I still have 2 minutes. I think I can finish it. Oh, great. Go to the. So the quantum mechanics. It's more complicated, but it's still okay because, like you just think of that. you want to get something like square root 5, what you really want to do is that you consider two conditions in two different locations. Like for example, one in Chicago and one in New York, right? And there's the vertex, right? And like this, I will draw all of them. The idea is that you think about the product of the event, like both this one and this one happen. So mathematically speaking, you are doing a product graph. It's like you have two dice now, and that's something interesting. So what? Because initially you only have one graph, and there's exclusive relationship are very simple. Once you get something like what the V0 and U0 happen, you actually have, instead of 5, you have 25 events. It's like the first dice get number 1 and the second dice get number 5. You just like it's like 5 times 5. And what's the shape of that product? Product graph is something like this. It's okay because you find the complete graph. Sure.
I thought some of these combinations were exclusive though. So how can you have all 25 allowed when you have cases?
What's the question?
Because you have 5 V's and 5.
Yeah.
Oh, it's two different.
Yeah, two dice.
Yeah, sure.
And actually, we were considered is just a special case. The more generalized argument is because we still hold the exclusive event, the probability of the exclusive event can exceed 1. It's like if you only have like 1 rows, but maybe you have 3 ones and they are mutually exclusive, and 4. Right? And if you really look at this, it's not ugly like that. It's more like right? It's a complete form, complete graph for the 5 index, and the exclusive principle should tell you it's less than 1. So that's the point. And from the paper I want to talk about, they just found out those 25 events are just happen to be 5 groups, and those 5 groups have mutual exclusion. Those 5 groups are in the shape of the complete graph. So what you can get is like here, no?
Sorry, before you raise that, what do you mean by the complete graph is less than 1?
Complete graph.
Yeah, you said
so
what is less
like
than 1?
you have you have a dice and right, it has 6 values 1, 2, 3, 4, 5, a dice, right? They are mutually exclusive to each other,
yes,
to everyone.
Yeah.
So the probability of the summation of all of them should be less than 1.
Summation of probability of
Like
of
the
what?
summation of you get 0.1, the summation of you get 0.1, 0.2, 0.3, 0.5.
But why isn't it exactly equal to 1 in that case? How can it be less than 1?
Yeah, it's completely mutual.
Like if you just erase the 0.6, And
No, but in the case you gave of the dice with all sides are mutually exclusive, then the sum has to be one, because you specified all possible outcomes. Right? Whether exclusive or not is sort of a different issue.
I only need is less than one, and for the maximum value, it's probable to achieve.
Yeah, it's just, I think some of us are having trouble understanding the system that you have in mind when the sums of the probabilities is less than one and not equal to one. So what kind of situation are you talking about there?
I think when you do not have a complete picture of the system.
Right.
But, right.
Well, I mean, maybe if you take this die example, you can have an external factor, which is, let's say that the probability, so what you're saying is that if you roll the die, the probability that you get any number is 1, and the sums of the probabilities of getting any number is also 1.
Yeah.
But now let's add an extra factor, which is, now let me tell you that there's some probability that I won't throw the die. So that's that number, and then that can be less than 1. So if I only throw the die half of the time.
I don't understand what the point of that is.
I think what you're saying is the graph is complete. It's not that all the events are not complete. Like they are exclusive events, but not complete events. What he is saying is the graph is complete. So like all the pair.
What is, okay, but what is the point of the graph that's complete, but which doesn't represent all possible outcomes? What's the point? I'm missing the point. I'm not challenging, and I just don't understand where this is going.
For the if in life.
I'll talk to you.
And is it general true that the summation of probability is always less than 100%? You can't get the
If
summation
you
of
like
probability.
the classical probability view, it is like the portion of the something over something. So it's always less than 1.
Yeah, I mean, when you sum all over all the circumstances, the summation of the probability is always less than 1. That's true all the time, I think.
Yes.
So what's
Yeah,
the
that's
point
the
when you
principle.
mention that?
That's we don't want to make some weird principle. We want to deduce something inside. We want to deduce some insight from the very basic principle. Okay, so it's really like a graph theory in action. It really proves something. We use the graph theory. So what I just proved is that we have 2 different groups, however, in the product graph we have 25 events, right? So which means if we want to reach the maximum, each event in that graph should be 1/5 the probabilities. But remember that all of the vertex of that graph is a product of the probability something. And in order to reach the maximum, and you should think it's like this. So just the square root, imagine they are equal to each other. And since so after this point we can recover, and we can go back to the original no product graph. And since every one is this, and you just times 5, it can give you the square root 5. So that's the point. Yeah, it is really like 2 graph and the product graph, and going to this point and return to the individual graph and get the result. And it's good because it's in between, so it makes sense, right? So there's even experiment doing this kind of experiment to verify. But the final culture is that I need to prove this number is the lowest number, the the number are significant in the graph theory. In that sense, I can use the product graph approach and more, but I still can use it's like more like a maximal value approach. So just imagine that you are the state you really want to measure is a 3-state system. So it can be like in the space you are measure the angular momentum, or generalize the 3-state system. And you prepared your state in the z direction. And how will your ABC be is like different direction of measurement. I mean the configuration of the direction of the measurement can be. Some people just construct this. It's like the V0 to V4 can be those vectors. So imagine a vector there, and there's different vectors, and you do the projections, and a lot of algebras, and finally you get the same answer. It's just like it's the same answer as we use the product graph approach. So I already proved it's 35. Why I still want to bring this approach? Because that's the point of the lawless number. It's just really like you have a state vector point to a direction, and you have the freedom to rotate this state vector, and you also have the freedom to deploy your different ABCD vectors, the position, I mean the direction of the measurement, and you try to reach the maximal value. And that's the very definition of the lawless number. It's just this. Also under the constraint, the mutual exclusive even can say one. So that's the main body of my talk, and it's all summarized here. A personal comment, not personal comment. A comment is that if you really think about this, it's nice because physics and math are always correlated to each other, and you think about how the Newtons come, the calculus, and how the Riemann geometry as the operation system, and the general relativity as the application for that operation system. The same story happened here. The graph theory as the operation system, and the quantum correlation as the application. I might talk to the Professor Schmidt before, and he said I have a taste for the math, and I'm shocked. I don't understand that at that point, but now I realize it might be true. And actually, I also like the computer science is my favorite subject. It's also come into this journey because you really think about this. For the classical generalized and the quantum mechanics, you always finally want to define an algorithm to reach the maximum value, right? The independent number is the maximum set of the vertex of blah blah blah, and the general theory is the max of something. The quantum mechanics, the lowest number is also the max of something. It's just you need to define an algorithm to brute forcefully go into all the situations and try to find the maximal value, like simulate annihilation or whatever method you want to use. So the answer for this question is this. Actually, it's more like we really want a local theory. We don't want something disturb our interpretation of the causality. But quantum mechanics is weird and is subtle and it's not always like that. And the quantum correlation is kind of the key for this question. My reference and thank you, everyone.
Okay, so anybody has any more questions? So I'm actually speaking next week, and I'll talk about something much more boring than that. But I'll go back to the stuff that Kevin was talking about, in the sense of asking about neutrino interactions and how they get constrained by cosmology. But I'll concentrate more on a practical issue of whether it's possible for there to be new light, neutrino-like degrees of freedom that are consistent with what we know about cosmology. So that's what I'll talk about.
So if we have time to read only one of the 4 papers.
So yeah, so I was going to say something about that. There were several papers that came out around 2013. So I would recommend looking at those two, the two 2013 papers. They're both short. I think they're both letters, and they talk about the general idea. And the other more recent ones are sort of building on this.
And are we meeting here?
I think we're meeting on the other one.
No, we're back there, yeah. There's another date that will be in here. It's whatever the day of the holiday party is. That's on the spreadsheet though.
You mean we're gonna miss the holiday party?
No, that's what they're saying.
No, it starts at, the holiday party starts at 6.
We're doing this before the holiday party.
We should have this after the holiday party.
Everyone, I still have the cookies and the tea. Yes, thank you.
The graph itself is complete. So for every 2 vertices, there's an end. So, but there, what I'm saying is like, complete